Welcome to this coding walkthrough. Today, we'll be diving into problem number 214, titled Shortest Palindrome. This problem tests your ability to work with strings and develop efficient algorithms. Stay tuned as we explore the details and approaches step by step. A palindrome is a word, phrase, or sequence that reads the same backward as it does forward. In this problem, we are tasked with converting a given string S into a palindrome by adding characters at the front of the string. The goal is to return the shortest possible palindrome that can be formed through this operation. The input is a single string consisting of only lowercase English letters, and its length can range from 1 to 100,000 characters. The output should be a single string representing the shortest palindrome obtained. For example, if the input is asakea, we will compute the result as the shortest palindrome derived by adding characters to the front. In the first example, the input string is asakea. To make this a palindrome, we can add the character a to the front. This transforms the string into asikoa, which reads the same forward and backward. Since this is the shortest possible modification to achieve a palindrome, it is the correct output. In the second example, the input string is ABCD. Here, we need to add DCB to the front of the string. The result becomes DBABD, which is a palindrome. Again, this is the shortest transformation that satisfies the requirements. In the third example, the input string is empty. Since an empty string is trivially a palindrome, there is no need to add any characters. Therefore, the output is also an empty string. This highlights how the problem handles edge cases like empty inputs. The key takeaway is that the solution must effectively handle strings of varying lengths and configurations while ensuring that the output is the shortest palindrome possible. Now let's consider the constraints and a few additional edge cases. The string S has a length constraint between 1 and 100,000, and it only contains lowercase English letters. For a single character input, like a, the output is simply a because a single character is inherently a palindrome. Similarly, if the input string is already a palindrome, such as racecar, no additional characters are needed, and the output is the string itself. For an empty string, the output remains empty as explained earlier. Finally, if the input is a long string that is not a palindrome, such as ABCDEF, we need to add all preceding characters in reverse order to the front. For example, adding FETBA to ABCDEF results in FETBAPDEF, which is a palindrome. This ensures that the transformation is minimal while still achieving the desired result. Handling these cases efficiently is crucial, particularly given the constraint that the length of the input can go up to 100,000 characters. To solve the shortest palindrome problem, we can start by considering a brute force approach. The intuition here is straightforward. We check all possible prefixes of the string to find the longest prefix that forms a palindrome. Once identified, the remaining suffix of the string, which is not part of this palindrome, is reversed and added to the front to form the shortest palindrome. The steps involve iterating through each prefix of the string, verifying if it is a palindrome, and keeping track of the longest valid prefix. Finally, we reverse the non-palindromic portion and prepend it to the original string. However, this method comes with trade-offs. Its time complexity is O(n) squared, since we repeatedly check for palindromes, and each check takes O(n). While simple to understand, this approach is inefficient for larger strings because of its nested operations. Now, to improve efficiency, we can use an optimized approach based on the Knuth-Morris-Pratt algorithm, or KMP. This method relies on constructing a new string by concatenating the original string S, a separator like hashtag, and the reverse of S. From this concatenated string, we compute the longest prefix, which is also a suffix, or LPS, array. The LPS value at the last index tells us the length of the longest palindromic prefix in the original string. With this information, we can identify the remaining portion of the string that needs to be reversed and prepended. The key insight here is that the concatenation of S with its reverse ensures the LPS computation captures the palindromic structure, while the separator prevents false matches between S and its reverse. This approach achieves linear time complexity, O(n), for the LPS computation and requires O(n) space for the concatenated string and LPS array. There are trade-offs to the KMP approach, as it requires familiarity with the algorithm and careful implementation. However, it is optimal for this problem, avoiding the inefficiencies of nested loops. Alternatively, a simpler method involves using a two-pointer technique. Here, one pointer starts at the beginning and the other at the end of the string. The aim is to find the longest palindromic prefix by shrinking the right pointer until the prefix forms a palindrome. Once identified, the remaining portion of the string is reversed and prep-ended. While this method is easier to implement than KMP, it still involves nested operations since checking for a palindrome takes O(n) time for each decrement of the right pointer. This results in a time complexity of O(n squared, making it less efficient for longer strings. The KMP-based solution stands out as the most efficient choice. It reduces the problem to finding the longest palindromic prefix, and the LPS array provides a direct and efficient way to achieve this. By constructing the concatenated string s plus hashtag plus reverse s, we ensure that the process is both seamless and accurate, without false matches. Compared to the brute force approach, this method avoids redundant palindrome checks and improves the complexity from O(n squared to O(n). Similarly, it outperforms the two-pointer technique by eliminating repeated palindrome validations, leveraging the pre-computed LPS array instead. While the KMP approach requires understanding of the algorithm and slightly higher space due to the concatenated string, it strikes the best balance between clarity and performance, making it the ideal choice for solving the shortest palindrome problem efficiently. In this problem, we aim to convert a given string into the shortest palindrome by adding the minimum number of characters to the beginning of the string. A palindrome, as we know, reads the same forward as it does backward. To achieve this, one approach is to identify the longest prefix of the string that is already a palindrome. Once we find this longest palindromic prefix, the remaining characters, which are not part of the palindrome, can be reversed and added to the beginning of the string to form the desired result. Here's how the brute force approach works. First, we initialize by starting with the given string and keeping track of the length of the longest prefix that is a palindrome. Then, we iterate through all possible prefixes of the string, starting from the full string and working our way down to smaller prefixes. For each prefix, we extract the substring and check if it is a palindrome by comparing it with its reverse. If the substring matches its reverse, it qualifies as a palindrome. Once we identify a prefix that is a palindrome, we record its length, which we'll refer to as longest_palindrome_length. We continue this process for shorter prefixes until we determine the longest palindromic prefix. Next, we handle the characters that are not part of this palindrome. These remaining characters, which start from the index longest_palindrome_length to the end of the string, are reversed and then prepended to the original string. The resulting string, after this operation, becomes the shortest palindrome. The key to solving the problem is ensuring that these steps are performed accurately, as this guarantees that we're adding the fewest characters possible to achieve the desired palindromic structure. A few key insights help deepen our understanding of this problem and its solution. First, the fundamental property of a palindrome, that it reads the same forward and backward, simplifies the process of verifying whether a substring is a palindrome. By simply reversing the substring and comparing, we can efficiently check for this property. Second, while the brute force method involves iterating through every prefix, there are more optimized techniques, such as using the Knuth-Morris-Pratt (KMP) algorithm or hashing, that can find the longest palindromic prefix in linear time, improving the efficiency of the solution. Finally, we should consider some edge cases. An empty string trivially results in an empty palindrome, and strings that are already palindromes require no additional characters. Single character strings are also inherently palindromic, so no modifications are needed in those cases. In terms of implementation, the algorithm primarily relies on string manipulation, such as extracting substrings and reversing strings, which are supported efficiently in most programming languages. We use variables like longest_palindrome_length to track the length of the longest palindromic prefix and intermediate substrings for checking palindromes. Analyzing the complexity, the brute force approach involves checking each prefix, where each palindrome check takes linear time. Since there are n prefixes to check in the worst case, the overall time complexity is O(n squared). As for space complexity, the algorithm requires O(n) space for storing intermediate substrings and the resulting palindrome. Let's walk through some examples to see the algorithm in action. First, consider the string s equals ASIC. Checking its prefixes, we find that A and AA are palindromes, but AAC is not. Continuing further, we find that asakea is a palindrome, and since the remaining string is empty, no characters need to be prepended. The result is asakea, which is already the shortest palindrome. Now, take s equals abcd. The longest palindromic prefix here is a. The remaining string, bcd, is reversed to form dcb and prepended to the original string. This gives us dbabt, which is the shortest palindrome for this input. These examples illustrate how identifying the longest palindromic prefix and handling the remaining characters ensures the solution is both correct and minimal. Here, we begin implementing the solution to find the shortest palindrome. First, we create the reverse of the given string s using Python slicing with s::-1. This reverse string will help us identify how much of the original string is already a palindromic prefix. Next, we concatenate three components: the original string s, a delimiter hashtag, and the reversed string. This delimiter ensures that there's no overlap or ambiguity during the computation of the longest prefix that matches a suffix. After forming this temporary string, we compute the KMP table, also known as the longest prefix suffix, LPS, table, using a helper function compute LPS. This table helps us determine the length of the longest palindromic prefix in the original string. Finally, we calculate the characters that need to be added to the front of the string to form a palindrome. To do this, we take the portion of the reversed string that doesn't overlap with the palindromic prefix and prepend it to the original string. The result is returned as the shortest palindrome. Now, let's focus on the helper function compute LPS, which constructs the longest prefix suffix table. This table is essential for efficiently finding the longest prefix of the string that is also a suffix. We initialize the LPS array with zeros and start with a length variable set to 0, representing the current matching prefix length. The process begins at index 1 of the pattern and iterates through the string. If the character at the current index matches the character at the current prefix length, we increment the length and assign it to the current index in the LPS array. If there's no match, and the length is not 0, we backtrack using the previously calculated LPS values to find a smaller prefix that might match. If no suitable prefix is found, we set the current LPS value to 0 and move to the next character. This process continues until the entire pattern is processed, and the completed LPS array is returned. The LPS table plays a critical role in determining the longest palindromic prefix efficiently. Here, we begin by defining the shortest palindrome method, which takes a string s as input. The goal of this method is to find the shortest palindrome that can be formed by adding characters in front of the input string. To achieve this, the first step is to reverse the input string using a string builder and store it in the variable reverses. Next, we construct a temporary string temp by concatenating the original string, a delimiter hashtag, and the reversed string. This delimiter ensures there's no accidental overlap between the original string and its reverse during the computation. The key part of the solution involves computing the longest prefix suffix, LPS, table for the concatenated string using the compute LPS method. The LPS table helps identify the length of the longest palindromic prefix in the original string. Using this value, we determine the minimum characters needed to prepend, which are extracted from the reverse string and added to the front of s to form the shortest palindrome. The compute LPS method is a helper function that calculates the longest prefix suffix table for the given pattern. This table is essential for efficiently finding the longest palindromic prefix in the concatenated string. The method starts by initializing the necessary variables, n, which is the length of the pattern, an LPS array of size n to store the computed values, length to track the current matching prefix length, and I to iterate through the pattern. Inside the while loop, we check if the current character matches the character at the current prefix length. If it does, we increment length, store the updated value in LPS, I, and move to the next character. If there's no match, we check if length is non-zero, in which case we fall back to the previous prefix length using the LPS array. Otherwise, we set LPS, I, to 0 and move forward. This process continues until the entire pattern is processed, and the completed LPS array is returned. To solve the problem of finding the shortest palindrome, we'll start with an example where the input string is asakea. The first step is to reverse the string, which gives us asika. Next, we create a concatenated string by combining the original string, a delimiter symbol like hashtag, and the reversed string. This results in asika #asika. Once we have this concatenated string, we compute the longest prefix suffix, LPS, array using the compute LPS function. The LPS array helps us identify the longest prefix of the string that is also a suffix. We begin by initializing an array of zeros, LPS equals 0, *len, temp, and two variables, length equals 0 and I equals 1. As we iterate through the characters of temp, we compare the current character with the character at the length index. For example, at index 1, the characters match, so we increment length to 1 and set LPS 1 equals 1. If the characters don't match, we reset the length based on the LPS values. This process continues for all indices, and at the end, we have the LPS array as 0, 1, 0, 0, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, but. From the LPS array, we can determine the length of the longest palindromic prefix, which is given by the last value in the array, LPS-1 equals 8. Using this value, we can construct the shortest palindrome by adding the minimum required characters to the front of the original string. In this case, the prefix length already equals the length of the string, so no additional characters are needed. The result is simply the original string, asika. Now, let's look at another example where the input is ABCD. After reversing the string, we get tkba. Then, we create the concatenated string, which becomes ABCD #tkba. Next, we compute the LPS array for the concatenated string ABCD #tkba. Similar to before, we initialize the LPS array and the two variables, length equals 0 and I equals 1. As we process each character, we find that no prefix matches any suffix for this particular string. This results in an LPS array filled with zeros, 0, 0, 0, 0, 0, 0, 0, 0, 0. The longest palindromic prefix length is therefore LPS-1 equals 0. With this information, we construct the shortest palindrome by adding the reversed portion of the string, excluding the prefix part. Specifically, we take reverse _ len s longest _ palindromic _ prefix, which is DCB, and prepend it to the original string, ABCD. The result is dbabbed, which is the shortest palindrome. For another example, consider the input string rayscar. The reverse of this string is likewise rayscar, and when we create the concatenated string, it becomes rayscar #rayscar. Moving on to the LPS computation, we process each character of the concatenated string. Here, we find that the LPS array gradually builds up as the prefix of the string matches the suffix. The final LPS array is 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7. The last value in the array, LPS-1 equals 7, indicates the length of the longest palindromic prefix. Since the input string rayscar is already a palindrome, no additional characters are needed to construct the shortest palindrome. The formula reverse _ len s longest _ palindromic _ prefix plus s gives us an empty string concatenated with rayscar, resulting in the output rayscar. This confirms that the original string is the shortest palindrome it can be, as no modifications are necessary. In analyzing the time complexity of the algorithm for solving the shortest palindrome problem, we start by breaking it down into its major steps. First, we reverse the string s using slicing, which is an O-N operation because it processes each character of the string individually. Next, we concatenate three components, the original string s, a delimiter hashtag, and the reverse string reverse _ s, to create a temporary string temp. Since the length of temp is approximately 2n plus 1, this step also takes O-N time. Following that, we compute the longest prefix suffix, or LPS, array for the temporary string using the Knuth-Morris-Pratt pre-processing algorithm. This step involves iterating over the characters of temp, and the time complexity of this step is O-M, where m is the length of the temporary string. Since m is approximately 2n plus 1, this simplifies to O-N. In summary, the dominant time complexity contributions for these steps align at O-N. After computing the LPS array, the final step in the algorithm is to construct the resulting string. This involves extracting a substring from the reversed string and concatenating it with the original string s. Both substring extraction and string concatenation operate in O-N time, as they depend on the length of the input string. When we consider the total time complexity of the algorithm, the most time-intensive step is the computation of the LPS array, which is O(n). The other operations, string reversal, concatenation, and substring extraction, also contribute O(n) each, but they do not change the overall asymptotic complexity. Therefore, the final time complexity of the algorithm is O(n), making it highly efficient for this problem. Now, looking at the space complexity of the algorithm, the major contributors are the auxiliary data structures and temporary variables. First, the LPS array, which is constructed during the KMP preprocessing step, requires O(m) space, where m is the size of the temporary string temp. Since m is approximately 2n plus 1, this simplifies to O(n). Additionally, the algorithm creates two temporary strings, reverse_s, which stores the reversed version of s, and temp, which combines s, the delimiter, and reverse_s. Together, these strings contribute O(3n plus 1) space, which simplifies to O(n). Apart from these, only a few scalar variables, such as length, I, and longest_palindromic_ prefix, are used, and their space usage is constant, or O(1). When we combine these factors, the total space complexity of the algorithm is dominated by the LPS array and the temporary strings, resulting in a final space complexity of O(n). To put the optimized solution into perspective, let's compare its time and space complexities to those of a naive or brute force approach. In the naive method, we would repeatedly check if successive prefixes of the string are palindromes and append characters to form the shortest palindrome. Checking palindromic properties for each prefix could take O(n squared) in total, making the overall time complexity O(n squared). The space complexity, on the other hand, would still be O(n) for storing any additional characters. In contrast, the optimized solution using the KMP algorithm reduces the time complexity to O(n) by efficiently finding the longest palindromic prefix through the LPS table, while maintaining the space complexity at O(n). This makes the KMP-based approach significantly faster without increasing space requirements. To summarize, the optimized approach achieves linear time complexity while matching the space efficiency of the naive method, making it a clear improvement overall. When solving the shortest palindrome problem, there are several common mistakes to watch out for. First, edge cases like an empty string, a single character string, or strings with all identical characters are frequently overlooked. These cases might seem trivial, but failing to handle them can lead to runtime errors or incorrect results. For instance, if the input is an empty string, your algorithm should gracefully return an empty prefix without unnecessary computation. Another common pitfall is implementing a brute force solution that checks every possible prefix and suffix combination without optimization. This approach can quickly become inefficient, especially when the input size grows large. Think of cases where the string length approaches 10,000. Similarly, incorrectly verifying palindromes can also cause inefficiencies. While reversing a string or using basic comparisons might seem straightforward, techniques like the two-pointer approach are both faster and more reliable. Lastly, repeatedly modifying the input string, such as constructing new substrings during each step, can unnecessarily increase space complexity. Instead, aim to work directly on the original string as much as possible to keep your solution efficient. Assuming specific constraints, such as only lowercase letters in the input, is another trap you should avoid. Always check the problem description carefully for the full range of valid characters, which might include uppercase letters, numbers, or even special characters. Overlooking this can lead to solutions that fail for certain edge cases. Now, in terms of interview strategy, recognizing patterns is key. Many palindrome problems, including this one, rely on symmetry, so techniques like the two-pointer approach or dynamic programming can be highly effective. Additionally, optimization is crucial. Pre-computing results or leveraging prefix and suffix properties can significantly reduce redundant calculations. When discussing your solution, make sure to explain the trade-offs clearly. For instance, while brute force might be simple to implement, it's not scalable for larger inputs. Finally, interviewers often test your ability to handle edge cases, so be prepared to explicitly discuss how your algorithm addresses constraints like empty strings or special characters. This demonstrates a thorough understanding of the problem. The shortest palindrome problem is closely related to several other problems that you might encounter. For example, LeetCode 5, the longest palindromic substring, focuses on finding the largest contiguous palindrome within a string. LeetCode 9, palindrome number, shifts the context to checking whether a number reads the same backward as forward. Then there's this problem, LeetCode 214, and LeetCode 131, palindrome partitioning, which explores breaking a string into the smallest possible palindromic segments. These problems share similar themes and techniques, making them useful practice for building your understanding of string manipulation and symmetry. Now, when it comes to approaches, a brute force method might be where you start. It's simple to implement but computationally expensive, with time complexity of O(n) superscript 2, or worse. While it's a good baseline to verify correctness, it's not practical for larger inputs. The two-pointer technique, on the other hand, offers a much more efficient solution with O(n) time complexity. It minimizes space usage and is great for verifying palindromes, though additional logic may be needed for prefix or suffix handling. For a more advanced and optimized solution, the Knuth-Morris-Pratt algorithm, or KMP, is highly effective for problems involving prefix and suffix matching. While it has a time complexity of O(n) and is optimal for certain cases, it does require a solid understanding of pre-processing patterns, which can make it trickier to implement. Finally, we have Manicher's algorithm, which is another advanced strategy specifically designed for palindrome problems. With a time complexity of O(n), it's incredibly efficient, especially for tasks like finding the longest palindromic substring or solving variations of this problem. However, it's worth noting that Manicher's algorithm involves a more complex implementation process, which can make it harder to explain during an interview. While it's an excellent tool to have in your arsenal for competitive programming or optimizing solutions, it's important to weigh whether its complexity aligns with the interview scenario. Often, simpler solutions that are easier to explain and adapt are more effective in that context. By understanding these various approaches and their trade-offs, you'll be well equipped to tackle not only this problem but also other palindrome-related challenges with confidence. Great job making it through the problem. We reviewed key strategies and concepts for solving problem number 214, shortest palindrome. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!